Hello everyone and welcome to the second video of Creating Descent Algorithm series. Now we need to change our denotions a bit, and in the last video I said that the output of this equation is called predicted species. Now we'll name it as y hat. The predicted species is called y hat according to the set standards. Another thing that we need to change is that I call it an error function. This is another function, and I said that this is called an error function. This calculates the error. Actually, this calculates the cost function. It's called the cost function, and it calculates the cost. Error and cost are the same things. Another thing that we need to change here is that we named the the variables in the error function or the cost function as actual species and predicted species. Predicted species is changed to y hat, as you can see above. So we'll change that to y hat, as you can see in the equation below. It's the same equation as above, but it's simplified. Predicted species is written as y hat and the actual species is written as y. So this function has a graph like this. The cost function has a graph like this, and it has C on the y-axis, cost on the y-axis, and WK on the x-axis. Now what is WK? As we had 5 weights in our equation, so we cannot generalize we cannot specifically say that we are talking about W0, W1, W2, W3 or W4. We need to look at them generally first. So I named it WK, and this function is shaped like this. It has a minima. Now do you remember a function from your early school days? Y is equal to x square. Y is equal to x square. It used to be somewhat like this. Let me redraw this. It used to be like this. So it also had a minima, and we had y on our y-axis obviously and x on our x-axis obviously. This function has quite a similar shape here. So why does it seem very similar to this function on the right hand side? That is because in the cost function, as you can see, there is an expression y minus y hat whole square. So it's the same thing basically, because a variable or a combination of variables is being squared, and that is why the function is shaped like this, and we have wk on our x-axis. So why do we have wk on our x-axis, and where is wk in this equation? So this equation has the variable y hat, and y hat is equal to the combination of weights. This equation is a combination of each weight multiplied by feature and a featureless weight, which is w0. So y hat had weights in it, and that is why this equation can be represented in the form of weights. Cost function can be represented in the form of weights. And now we need to change our weights in such a way, we need to alter our weights in such a way that these weights are minimizing our cost. For instance, let's assume that we are at this point and our weight is 2.8. Our weight is 2.8. So let me change the color first and the brush size. So this is our weight, which is 2.8, and let me draw a straight line. And let's assume that the cost for this value is 10. Now what do we need to achieve here? As I said in the last video, that the weights should minimize the cost. So to minimize the cost, we should be reducing our weight. The weight should be reduced a bit in such a manner that it approaches this value. The weight, we have to calculate the weight in such a manner that we approach this point. Now this is a very ideal scenario. We cannot reach this point in every scenario, but that is the target value which we have to approach. Even if we are at this side, let's assume that we had a value of 1.5, and Our cost is 8. So to decrease our cost, now we have to increase our weight. As you can see that the x-axis is increasing to the right, obviously, and we have to increase our weight to reach this point. And if we are at this point, and if our weight is 2.8, we have to decrease the weight to reach this point. So basically the idea behind this is that we have to decrease or increase our weight to adjust that in such a way that it is minimizing the cost. Now what is that value which should be added to the existing value of weight to change that in such a manner that it approaches this value? So that value is this one: training rate multiplied by partial derivative of cost with respect to wk. Now wk is a general form of weights here. When we'll be calculating the weight, we'll be calculating this equation separately for every weight. So what is training rate? Training rate is the rate at which we want this weight to be updated. As you can see that wk bar is the new updated weight, wk is the old weight, and the old weight is in this equation because the training rate multiplied by the partial derivative of cost with respect to wk is being subtracted from the old weight, and this gives us the new updated weight. So the training rate is set somewhat like it can be 0.0.1 or it can be 0.0.1. It is set during the program. It is set when you run your program, and then you set that accordingly. There is no definite value which is recommended. You have to train your program and you have to see what suits best for your program. So that is set during the algorithm when you are writing the code for it. So now we'll be specifically addressing w1 here instead of wk. We'll be moving to the specific weight w1. w1 was a weight which was attached to sepal length, and this weight is, the formula is same as above. The above formula is copied below and k is replaced by 1. So the updated weight formula is w1, the new updated weight w1 bar is equal to old w1 minus training rate times partial derivative of cost with respect to w1. Moving to the function partial derivative of cost with respect to w1. So how can this be calculated? Now this will be calculated using the chain rule. As we have our cost function and our y-pred function, this is our y-pred function or y hat function. This one right here is our y hat function, and this is our cost or c function. So this is a cost function. We have both of these functions, and these two functions can be written in the form of weights. So this partial derivative of cost with respect to w1, which is being used in the weight update formula, as you can see that this thing is being used in the weight update formula, and we need to calculate this to use that in weight update formula. So this will be calculated in such a manner that we'll be using chain rule to calculate this, and the chain rule states that partial derivative of cost with respect to y hat times partial derivative of y hat with respect to w1. That leaves us with partial derivative of cost with respect to w1 as it's written on the left hand side of the equation. So partial derivative of cost with respect to y hat is what we need to calculate first. This first expression is what we need to calculate first. So partial derivative of cost with respect to y hat. Now our cost function is this one, and this right here is a cost function. Cost is equal to 1 by 2 times summation of 1 to the number of samples times real y minus predicted y squared. And to calculate its derivative with respect to y hat, we'll simply be, obviously 1 by 2 is a constant, so it will stay as a constant. 2 is being this expression is being raised to the power 2. For instance, if you had summation of x square, what would you do with that if you would have to take a partial derivative of x square with respect to x? You'd have moved 2 as a constant to the left hand side of x. Likewise, I'll be moving this 2 to the left hand side of y minus y hat squared, and obviously this will be written outside the summation sign. As it's a constant, it can be written outside the summation sign. So this expression stays inside, and then we also have to take the derivative, partial derivative of this expression, which is partial derivative with respect to y hat, as we are taking the overall derivative with respect to y hat. So this will also be taken according to with respect to y hat of this expression y minus y pred or y hat. So this will be simplified, and this will be written as 2 is gone now, as it is simplified, and we are left with summation of 1 to n. It's written summation of 1 to n y minus y pred or y hat whole squared multiplied by minus 1. Now where is this minus 1 coming from? When we are taking a partial derivative, everything is set to everything is considered as a constant except the variable with which uh, with which we are taking the partial derivative, with respect to which we are calculating the partial derivative. So we are calculating the partial derivative with respect to y hat. So this is not a constant. Every other thing is a constant. Now y is let's assume that y is a constant. So when we take its derivative, it is obviously 0, and we are left with minus y hat, and and the derivative of y hat is obviously 1, as we are taking the derivative with respect to that. So that gives us minus 1, and this is the value for partial derivative of cost with respect to y hat. Moving over to the second function, which is partial derivative of y hat with respect to w1, this one, partial derivative of y hat with respect to w1. Now do you remember this, the predicted species formula? We named the predicted species output as y hat and replace that here. The formula is same. Now instead of naming these features separately, we'll be denoting these features by I. Now sepal length is I1, sepal width is I2, petal length is I3, and petal width is I4. So as we are taking the partial derivative of y hat with respect to w1 only, so everything will be set to constant, will be considered as constant except w1. So w1 is not a constant here. w1 is the variable whose derivative we have to calculate here. Every other thing is set as constant. Now let's assume that I1 is a constant and W1 is a variable with respect to which we are deriving, with respect to which we are derivating this equation. So I1 times W1, as W1 is the variable with respect to which we are calculating the derivative, and I1 is a constant, so we will be left with I1 only. And all other variables in the equation above are constants, so those will be equated to 0. W0 is set to 0, W2 and sepal width, W3 petal width, W4 petal width, everything is set to 0 here. And sepal length, sepal width, petal length, and petal width are obviously constants, and these other variables W1, W2, W3, W4, all of these are set to 0, as these are constants. So we are left with I1. We got the answers to both of these equations now. The partial derivative of cost with respect to y hat is this one right here, this one, and partial derivative of y hat with respect to w1 is I1. So the partial derivative of cost with respect to w1 is equal to this expression which was written above, and as we came to know that partial derivative of cost with respect to y hat is actually equal to this one, and partial derivative of y hat with respect to w1, this one, is equal to I1 as we calculated above. So now we'll have to replace this part in our weight update equation, and we'll be done with the gradient descent algorithm. That is the idea of gradient descent algorithm. So let me copy this right here, and we'll replace this part, partial derivative of cost with respect to w1, with the equation above. Let me erase this, or let me take the brush here. I'll remove this part. And I'll select this one, and I'll replace this part with the part which is removed. So this is a weight update formula for W1 only. Now obviously for weight 2 everything will be similar to this equation except this part. This part right here will be changed to I2. What does I2 mean? What does I3 mean? And what does I4 mean? These I's are the features, the value of features, the input values. In the Excel sheet, these are the values. This is I1, this is I2, this is I3, and this is I4. For every sample we have different I's, we have different feature values, and these feature values, these constants, obviously now we have these values, so these are uh, integers, so we'll be replacing these integers in the formula, we'll be putting these as input in the formula. Y is the real Y, which is, if it's a versicolor for instance, we decided that it is 1, so Y is 1 here. Y hat is calculated using the equation above, this equation. Y hat is calculated using this equation. Now the question which might bother you is that what are our initial weights? The initial weights are set randomly. You can take any values, any 5 values here. W0 is equal to 1, W2 is equal to 0, W3 is equal to 1, W4 is equal to 0, and so on. If you have 5 weights, 6 weights, 7 weights, you can take random values, or you can set those equal to 0 and 1, 1 or 2, and then you will be training those values, you will be updating those weight values using this weight update formula. So I guess we are done with the gradient descent algorithm.